In this video, we're going to look at how to calculate the size in base pairs of a DNA band on an agarose gel. So say you're working in a lab and you run an agarose gel, and in one of the lanes you've put a DNA ladder which contains DNA fragments of known sizes, and in another lane you've run a DNA sample which contains your DNA fragment of unknown size, and you wish to determine the size of that band. Now once you've imaged the gel, you need to label it up, and the first thing I do is I put the lane numbers across the top. So lanes 1, 2, 3, 4, 5 and 6, with lane 1 in this case containing the DNA ladder and lane 2 containing my unknown sample. I also label up the DNA ladder. As you can see here, this DNA ladder runs from 14,500 base pairs down to 150. Now we need to start collecting data from the gel, because what we want to do is plot a calibration curve. Now we know the size of the DNA fragments in the DNA ladder, so we put that into a table and we convert these sizes to the log value. The reason we do this is because when we plot the graph, this means we will get a straight line as opposed to a curve. Next we start measuring the distances that the bands in the DNA ladder have moved. So the first band there, if we measure from the center of the well to the center of the band, has moved 22 millimeters. The second band has moved 27 millimeters. The third band, the 9,000 base pair band, has moved 30. The 7,000 band has moved 37, and the 5,000 and onwards we just measure them and fill in the table, as you can see here. Finally, we measure the distance that our unknown band has travelled, and that is 58 millimeters. Next, we need to plot the graph. Now we want to make the best use of our graph paper. So what I have done here is, on the x-axis I have put the thing that we know, which is the log base pairs, and I've used a range here, so I'm making maximum use of the graph paper. If you look at the log values, they start at 2.1 and go up to 4.1, so I've got a range here of 2 to 4.2. Up the y-axis we put the distance that's been travelled in millimeters, and if again we look at the table, we see that a good range here is from 0 to 110. It's critical also that you label the axes, so I've got my log 10 base pairs along the bottom and the distance up the side. As I said, you always put the thing you know along the bottom of the graph. Next we plot the points, and then we add a line of best fit so that the points are equally balanced on either side of that line. Finally, we give the graph a title: Graph of Distance Against Log 10 Base Pairs. For the title, you always put the thing that you're measuring first, followed by the thing that you know, which in this case is the log 10 base pairs. Now we know the band of interest, the band in lane 2, the one which we're trying to determine the size of, has travelled 58 millimeters down the gel. Therefore, we find 58 on the distance axis, we draw a line across until it intersects with the curve, the straight line on our calibration curve, and then we drop a line down to the log 10 base pair axis and read off the value, which in this case is 3.36. Now 3.36 isn't the size in base pairs of the band, it's the log value, so therefore we need to convert that back to a base pair size, and if we do the anti-log of that value, we get a value of 2,290 base pairs. So our band in lane 2, the one of which we're trying to determine the size of, has a size of 2,290 base pairs. And that's it. That's how you determine the size of a band on an agarose DNA gel.